Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchats, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first 3: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies, or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested, of course, and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture. Let me just introduce a very important concept now. So this is very important what I'm going to do now. So imagine you have something like this. You have a force F applied at this point A. All right? And imagine that you have now a force which I'm going to say is equal to minus F applied at a different point B. So these two forces, F and minus F, they have the same intensity, same norm, or the length of these vectors are the same, but they are opposite, right? So if I calculate the resultants of these forces, which is summation of all the forces, this resultant is going to be equal to 0, because they are symmetrical forces, they have the same norm, so they cancel each other, right? So we call this system of these two forces in these conditions, we call this a couple. All right? If you have two forces that are opposite, they have the same norm, but they are opposite, so that they cancel each other. These two forces, they form what we call a couple. Not difficult to memorize this, I think. So what I'm going to do now is I am going to calculate the moment produced by this couple, or by these two forces, about, for example, this point O. Okay? And in order to do that, I need, of course, to define my position vectors, right? I need to define this position vector connecting point O to point A. I will call it ROA. And I need to define this position vector connecting point O with point B. I will call it ROB. Okay? Everybody's following? So we have a couple, these two symmetric forces, and I'm going now to calculate the moment produced by this couple about point O, and that moment, MO, is equal to what? Is equal to the cross product of my position vector ROA with my force F plus the moment produced my position vector ROB times my force, which is minus F. You all agree with me? So, I have two forces here, F and minus F. I want to calculate the moment about point O. I just need to add the contribution of my force F to the moment plus the contribution of my force minus F to the moment, right? And now I can work this a little bit. I can say that I will have ROA minus ROB. So I'm sending this minus signal to the position vector. I can do that. And then I multiply this by F. Okay? And now, this ROA minus ROB, this term here, I'm going to say this is equal to my R vector, which is, or if you want, I can say this is going to be equal to RBA, which is a vector connecting point B with point A. So I am subtracting two vectors, and the result of that subtraction is this vector that you have here in red, RBA, connecting point B with point A. And then I can say that this is going to be equal to RBA, external product or cross product with my force F. Right? And one important conclusion is just a moment. One important conclusion is the result of the moment produced by this couple of these two forces, F and minus F, is going to be this cross product of a vector that only depends on the position between point B and point A. So basically what I'm saying is that we evaluated the moment about point O, but the position vector starting on point O does not appear there anymore. Right? So, yeah, someone was asking something. Question here, right? Yes.
See that F, is that the resultant force of
Sorry?
F? See that F?
F is the force.
Is the resultant force of F and F minus F?
Yeah, it's the same. Yeah, look from this equation. What we did was we sent this minus signal that you see here. We sent it here to the position vector, and then we said this is the distributive property, right? And then we just, if you multiply now ROA with F, you get this term. And then if you multiply ROB with F, you get this other term here, right? Okay, look at this now. Look what I'm going to do now. Imagine I want now to calculate the moment about this point, point C, a different point. I want to calculate now the moment produced by this couple about point C. So what do I have to do? Well, I have to connect point C with point A with this position vector. I will call it RCA. And I have to connect point B with point C, and I will call this position vector RCB. All right? And then, if I want to calculate the moment about point C, I will have to do it in a similar way. So I will have my position vector RCA, external with my force F, plus my position vector RCB, external with my force minus F. That will be equal to RCA minus RCB, external with my force F. And my conclusion is this is going to be, again, equal to RBA, external F. Which is an amazing result, right? Look at this. It doesn't matter, basically. So we obtained the same result as when we calculated the moment about point O. So it means what? It means it doesn't matter which point I choose to evaluate the moment produced by this couple. That moment will always depend on the position vector connecting the 2 points A and B where the forces are applied, cross product with my force vector F in the couple, right? This is a very important property of this couple. So it doesn't matter which point we choose to calculate the moment, we can always obtain the same result for the moment produced for the couple, which is RBA cross product with F. Right? So we are going to see on the second half of the lecture how we can use this very important property to solve our equilibrium of 3D rigid bodies. Without this, we cannot do it. All right? So we'll see that in the second half. Let's do a break now. 5 minutes maximum. We are a bit late. All right? So you did ask me some questions regarding. So one that was asked us just right now was, why did we get RBA and not RAB? So in this previous slide, we obtain here RBA. So why is it RBA? So basically a position vector starting at point B and going all the way to point A, and not the other way around. The reason is, and I'm going to do it here, you get this vector which is ROB connecting point O with point B, and you have this vector which is ROA. And then what we want to do is we want to do ROA minus ROB. Correct? And I can write this in a... So this is a subtraction of two vectors. I can write this as an addition of these two vectors. How I can say this is equal to ROA plus minus ROB. You all agree? And what I'm doing basically, so let me try to move this a little bit more here. So what I'm doing basically is, if I use this vector, this is my minus ROB. Agree with me? You all agree with me? So if I add these two vectors now, I need to draw parallel lines to these two vectors, and then this is going to be the result of my addition. So this is going to be RBA, which is equal to ROA plus minus ROB. Right? So this RBA that you have here in red is in fact, don't forget this is my point B, is in fact, this is my point B here, right? Is in fact a vector starting at point B and going to point A, right? Not the other way around. So that was one first question that you asked me during the break. The second question was, again, something regarding the moment. I was given this situation here in a 2D problem. If we have a position vector like this, if we have a force vector like this, the question was, we learned in A levels that we obtained a moment which basically is an anti-clockwise rotation. And if you think carefully what you are saying here, this anti-clockwise rotation, if you think this rotation is going to be about an axis which has the direction of my z-axis, right? It's going to be a rotation about z-axis. Agree with me? So, if you use your right hand and if you align this with the position vector, so let me try to do it here graphically. So you have the position vector and you have the force vector here, right? So when you calculate the moment, if you do, so let me see if I can draw the. If you align your fingers, your right hand, if you align your fingers with your position vector like this, and then if you try to rotate your fingers from R towards F vector, you rotate like this, right? So your thumb will give you the direction of your moment. Look at this. If my fingers are aligned with R, if I rotate now my fingers through F direction, like this, anti-clockwise in this case, my thumb will tell me my moment is in the Z direction, right? It's a rotation about an axis on the Z direction, right? Yeah?
This seems similar to the right-hand grip rule.
Yeah, that's it. Yeah, that's what I'm saying. Thank you for the English correction. That's exactly what I'm saying. Right hand rule. That's what I'm saying. So, right hand rule is you use your right hand, you align your fingers with the position vector, you rotate your fingers towards F, and then your thumb will tell you the direction of the moment. Z, right? So, that's how it works. Now, let's continue with... maybe I can use... Yeah?
Isn't a moment supposed to be an
there is a convention for the moments. I use the one that says if your moment rotates anti-clockwise, I assume positive moments. If they rotate clockwise, is negative moments. Right? But we will see many examples. All right? Don't worry with that. All right. So let's go back to this couple. The moment produced by a couple. So the conclusion is the moment produced by a couple is equal to the position vector connecting the two application points of the forces, cross product with the force. And this is we call this a free vector because this moment produced by a couple does not depend of point O, of point C, of point D, E, F. It doesn't matter. Is a moment is equal everywhere, right? It's a free vector.
You say that anti-clock is the negative moment?
Positive.
Positive. The clock one is
Yeah.
negative moment.
Yeah.
So what does it mean negative moment?
Okay. So let me give you an example here. Imagine this situation here. You have your x and y axis. And then imagine you have this. So x, y, your z is, if you apply the right hand rule, if you rotate x towards y, your z is outside of the whiteboard, right? So if you have a force here, like this one, and if this is your position vector, r, the moment you will obtain will rotate like this, right? Anti-clockwise. Right? And if you rotate like this anti-clockwise, you will have a vector in the z direction which has the same direction as the positive z. Isn't it? Don't you agree? Look, if you pull with this force, it will rotate about a z axis anti-clockwise, right? So if you rotate anti-clockwise around your z axis, you will move on the positive z direction. Isn't it? Isn't it? Look, haven't you guys never opened a bottle of wine? Okay, if you know the cork opener, right? If you rotate clockwise, the cork opener is going down, right? Into the cork, right? You are rotating clockwise, so you are going down, right? You can rotate clockwise. So when you rotate anti-clockwise, the cork opener is coming up, isn't it? So imagine you have a z-axis aligned with the cork. Positive z is on the upward direction. If you rotate anti-clockwise, you are coming on the positive z direction, right? So that's why I say when we have a moment anti-clockwise, and if that anti-clockwise rotation is the same direction as the z-axis, we use it as positive. Now suppose I have this situation now that my force is applied on this direction. Right? What happens here? What happens here is that my moment will now be a clockwise moment, right? Agree with me? So this moment will rotate in a clockwise direction, so I'm going to the negative z-axis. That's why you get a negative moment at the end. But the good thing is that's why I recommend you guys to always use the cross product. Because if you do this cross product, we can do it very quickly here. You get the moment is going to be equal to this, right? This cross product. The position vector is in the x direction. The force vector is minus f. In this case, agree with me? So if you do this external product, you get what? You get a vector in the z direction that is equal to minus rf. Here it is. Clockwise, negative moment in the z direction. So if you do the cross product, even in a 2D problem, you always get the result correct, automatically. You don't need to worry if it is clockwise, anti-clockwise. It comes out automatically. So I strongly recommend, it's not difficult, you just need to memorize this cross product rule. You put that in your head, then your life will be Very easy. Okay? So, I need to start now talking about, otherwise we don't have time, a very important issue now. So, I'm going to do the following. Imagine you have a 3D structure, a very generic structure. I represented the structure like that. And then imagine I have this point here. Let's say this is my point A. And at this point A, I have this force F applied at point A in my structure. Now imagine that I have here another point B, and I have this force P, for example, applied at point B. And I have a point C here with a force T, and so on. Imagine I have many different forces applied at different points of my structure. So I cannot just come here and say, well, my equilibrium equations is summation of forces equal to 0. Well, we will need this to study the equilibrium, but it's not enough. The reason is because all these forces, they are applied at different points. Not in a single point like we did last week for the equilibrium of a particle. So I need to have something more to study the equilibrium of 3D rigid bodies. And what I'm going to do is I'm going to start. So I'm going to delete this now, and I'm going to start with a very important procedure, which is I want to get an equivalent system to this one. So we have now this 3D rigid body with a force F applied at point A, and I want to get an equivalent system at point B where basically I want to replace that force in point A and move it to point B, but I want to maintain the equilibrium of the structure. I cannot destroy it. So how do I do that? So what I'm going to do is something like this. I'm going to include in point B a force F, the same force that I have in point A. I'm just going to copy that force to point B. But if I do only this, I am altering the equilibrium. I'm changing the equilibrium, right? This is not the same as the initial configuration with a force only at point A. This is completely different. So how do I make this the same? Well, I make this the same if I include a symmetric force here at point B minus F. Don't you agree? So if I add at point B a force F and a force minus F, they cancel each other, then I get exactly the same initial problem. But now you might be asking, why did you do all of that? It seems your system is much more complicated. You didn't simplify anything. Not yet, because if you look at this force F at point A and this force minus F at point B, they form what? A couple. Exactly. So we are going to focus on this couple now. What did I tell you about the couple? Summation of forces produced by a couple is equal to 0. So what I'm saying is that this force F at point A and this force minus F at point B, they will cancel each other, right? In terms of forces. But a couple introduces a moment. And how much is that moment? That moment is equal to the cross product of this position vector connecting point B with point A. So that the moment produced by that couple, I'm going to say M is equal to the position vector RBA external product with my force vector. This is exactly what we obtained in this
slide here when we calculated the moment produced by a couple. Position vector connecting the two application points of the forces of the couple, cross product with the force. Right? So, this is a very, very important result. Why? Because now I can say, so I can replace this couple, this F force and this minus F force, I can replace this couple with the moment M. I can say, I can do something like this. Look at this. I can remove this force F at point A. I can remove the force minus F at point B. And the only thing I need to do now is I need to include the moment produced by the couple, and that moment M is equal to RBA cross product with my force F. And then look what I have. So I'm going to write on the right hand side here, I'm going to try to draw the initial configuration we had before. So before we had at point A, we had this force F at point A. And then I can say that these two systems, they are equivalent. So having our original system, this one here on the right, with a force only, a force F at point A, is equivalent to this system on the left with a force F at point B and a couple M, which is equal to RBA to F. So what I did, if you look carefully, what I did was I transferred this force from point A to point B. But when I do this, when I transfer the force from point A to point B, I need to add the couple, the moment produced by the couple. Right? M, this M. So at the end I will have an equivalent system, force plus a moment produced by a couple. Right? And why is this important? Because, look now, imagine I have now a point C here with a force P. I can put in a different color with a force P. Imagine I have this my initial system. So point A and point C. I have a force F at point A, a force P at point C. So we transferred already on left hand side, we transferred already the force from point A to point B, and we added a moment as well. I'm going to do the same for this force at point C, force P. So what I'm going to do is I'm going to include a force P here. So this is my P. It's the same force as I have at point C, but I need to add a couple. I'm going to put it now in green. And this couple, M in green, is going to be equal to my position vector connecting point B and C. Let me zoom in a little bit. Position vector connecting point B and C. External product with my force P. Right? Of course, I can now add these moments, this green, the moment in green and the moment in red. I can add them together to have only one vector, total moment. I can do the same for the forces. I can add my force F and P and have a resultant force. And I can continue. If I have another force in a different point, I can also transfer everything to point B by adding the force plus a moment. Right? Why is this important? Because now, look what is going to happen now. I'm going to copy this guy. Copy. Paste here. Yeah. So what I'm going to say is that I'm going to, in this point B, I'm going to have a resultant of the forces. So this resultant of the forces, as you know, we talk about the resultant is summation of all the forces we have in the body, right? This is the resultant of the forces, and I'm going to put it here in red. I'm going to have as well, I'm going to say mr, a vector, which is a moment. So this mr is going to be as well a summation of all the moments. I can say Ri cross product with Fi. A summation of all the moments. In this case, it was going to be equal to the summation of the moment we have in green with the moment we have in red. So I add all these vectors together and I have a resultant for the moments as well. And then I will have this equivalent system at the right-hand side. This equivalent system here. And then you can see we have everything, forces and moments. On the right-hand side here, we have everything concentrated in one single point of our structure. And what are we going to do now to study the equilibrium? Well, I'm going to say the resultant of the forces, they need to be equal to 0 to be in equilibrium. So in a 3D problem, we have three equations. Summation of forces in x equal to 0. Summation of forces in y equal to 0. Summation of forces in z equal to 0. Three equilibrium equations. And I'm going to say the resultant of my moments also need to be equal to 0 to be in equilibrium. Right? Resultant of the moments also need to be equal to 0 to be in equilibrium. And then we will have three additional equilibrium equations. X component of the moments equal to 0. Y components of the moment equal to 0. Z components of the moment equal to 0. Just a moment. So what I'm saying is that we will have something like this. Resultant of the forces. We are going to have X components, Y components, Z components. They all need to be equal to 0. The resultant moment, at that point, we will have a component in the x direction, a component in the y direction, and a component in the z direction. They will all have to be equal to 0 as well. Yeah.
Why should the motion be 0?
It's the equilibrium equation for the moment. So when we studied the particles, we said summation of forces need to be equal to 0. The balance of the forces, right? I also give you an example, right? You see, we have to do the same for the moments. The moments, they need also to be balanced. All the moments you have in that point, they need to be in equilibrium, balance. So that means equal to 0. Okay. Yeah. So this is the equilibrium equations you have for a statics problem. So we are going to work. Do many examples now, and we have a lecture in the afternoon, right? We are going to do some examples, application of this. But what I want to emphasize is this procedure that we did. I'm going to summarize again because this is extremely important. So the situation is we will have a complex structure where we will have a complex geometry and we have many forces applied at many different points. How do we study the equilibrium of that structure? Well, before we start writing the equilibrium equations, we need to build an equivalent system force-moment. How do we do that? Well, we take advantage of the moment produced by a couple. The moment produced by a couple allows me to transfer a force from one point to another by adding a moment, the moment produced by the couple. So I can do that for as many forces I have in my structure. So at the end, I will have everything concentrated in one single point of my structure. This point can be any point you want, you choose for convenience. Of course, we are going to do many examples where I ask you explicitly, construct the equivalent system force moment in point A or in point O. I will ask you to do that. But when you are solving an equilibrium problem, this point B that we have here in the slides can be any point of your structure. What it means is that you need to concentrate everything in that point. The resultant of the forces and the resultant of the moments. Once you have everything concentrated in that point, then you can say, if this point is in equilibrium, or if these two vectors, resultant of forces and resultant of the moments, if they are equal to 0, then it means my entire structure is going to be in equilibrium, not only this point. That's the big advantage of this, because we built an equivalent system concentrated in one point. So basically, I transformed the equilibrium of a 3D rigid body into an equilibrium of one point. Of course, we have the moment there, but that is the big advantage of this procedure, okay? So let's do one quick example just to show you how this can be done. So I'm going to stop this one and start a new one. So in this example, you have this structure or this column here. You have basically 3 force vectors applied at 3 different points. Right? You have these 300 newtons here. These 300 newtons horizontal force applied at this point. You have these 500 newtons, this force in this cable that is applied in that point there. And you have another force here. So you have a 3D rigid body with 3 different forces applied at 3 different points. The question is, I want you to build the equivalent system, force, and couple moment, or moment, force moment, at point A, in this case, right? At point A. Right? So this is an example I took from the Ibler book, is this book here, which is the book we recommend for this model. Ibler is the name of the author. The title of the book is Engineering Mechanics Statics. You have many copies of this on the library. We follow this book, but you have also many different books in library, so you can just go there and grab some books and do some examples if you want. Okay. All right. So let's do this. So we need to build what? We need to build at point A. So basically, what I'm saying is, you need to have a resultant of the forces R, and you need to have a resultant of the moments MR. Okay? So let's start with the resultant of the forces. Let's do it here. So, resultant I just need to add all my force vectors that I have, right? So let's start with this one. Of course, we need to have a coordinate system. Let's say I will consider this to be my x-axis and this to be my y-axis. Okay? Z is perpendicular to these two. So this 300 newtons here, it only has a component in the horizontal direction, so I can say this is equal to minus 300, 0, 0. This force vector is this one, plus. I'm going to continue here below. Now let's do, for example, this one, this 500 newtons. You tell me how much is the horizontal component of this one? Minus 500. Cos 30, is it? The vertical component in the y direction? 500 sine 30. Z component is 0, right? And now the last one is this. You tell me horizontal component, 250. 4 over 5 times 4 over 5, is it? Is the sine of that angle, right? Is 4 over 5. Vertical component, how much is it? It's positive or negative? Negative. 250 times what? 3 over 5. Z component is 0. So it means we will have this resultant vector is going to be equal to, can you please do this? So you have minus 300 minus 500 cosine of 30 plus 250 4 over 5. How much is this, please? Can someone do the calculations for me?
Minus 533.
Minus 533. So I'm going to just replace that one here. Minus 533. That's it. Now the y component is 500 sine of 30 minus 250 times 3 over 5. How much is this, please?
100.
Huh? 100? Okay. It's positive, right? 100. Z component is 0. So this is our resultant of the forces. Let me just... Okay? You all agree with this? Now, for the moments, let me try to move this. Okay. Now, for the moments, we will have basically to calculate the moments about point A. Okay, we will, of course, we need to construct this couple. So let's do the couple one time and then we will do it in a quicker way. So let's do, for example, for this 300 newtons. So let's start with this one first, this 300 newtons. So let's build a couple for this 300 newtons. So in order to build a couple, what I'm going to do is, I'm going to add, so let me zoom in. I'm going to add this 300 newtons here. And then, of course, I need to add this minus 300 newtons in this direction, right? So where is my couple? My couple is this with this, right? And how much is that moment? So what is my position vector that I need? I need position vector connecting point A with this point here. I need this position vector in blue. Let's say this is my R1 position vector. I can say this R1. What is the x component of this position vector? 0. What is the y component? 1 meter. Z component, 0. And in order to have the moment produced by this couple, I need now to do the cross product of this with this force vector here, 300 newtons. What is the x component of this 300 newtons? X component, how much is it? Plus or minus? Minus. Y is 0, Z is 0. So this is the moment produced by these 300 newtons about point A. Let's see. Now, for the other forces, we can do a bit quicker. So I need to add now the moment produced by this force. Let's focus on this one now. So I need to add here. I need to include first the position vector. So starting at point A and going all the way until this point. This is my position vector, R2, let's say like this. I need to define this position vector. What is the x component? 0. What is the y component? 2. What is the z component? 0. Now I need to define this force vector here. X component, minus 500 cos 30. Agree? Y component, 500 sine 30. Very good. Z component, 0. So the moment produced by that force about point A is the result of this cross product. That is done as well. So the last one we have to do is this force. Now this one. Okay. So I need to add now. So my position vector, what is my position vector? My position vector is this one. Oops. Let me try to do it. This, wow, what's going on? This one here. So this is my R3. Yes?
The 500 Newton force do not take into account 0.2 meters.
Oh, you're right. Very good. I didn't see that. Sorry. So before we do this. So it is this, the force is fine, the position vector is not 100% correct, right? So we need to fix this guy here. So the position vector is this one, from here to here, right? Our R2. So let's say it is, you tell me then, x component, minus 0.2, y component, 2 meters, that is same, right? This is correct. Yeah, that's good. Thank you. Very good. Now, let's go back to our position vector, which needs to be this one, our R3, for this force. We are doing this 250 newtons now. The moment produced by this 250 newtons about point A. So position vector first, you tell me, x coordinate, 0.5, y coordinate, 3, z is 0. External product with the force vector, you tell me, x, I think force vector we did already, right? Is this one, right? You all agree with me, this is my force vector, so I can just copy this one, right? I can say it's 250, 4 over 5, minus 250, 3 over 5, 0. So if you do, so you have here this cross product you need to do, another cross product you need to do, another cross product you need to do. The good news is that it will have only component in the z direction. You can confirm that at home when you do these cross products, these calculations. And then this z component, this one here, this one here, you need to calculate at home. We don't have time for this. We can do this one eventually, which is very easy. This first one is 300, right? This second one, if you want, I can put this way. I can just write so minus 100 sine 30 plus 1000 cosine 30, and this one 0, 0, you will have minus 125 3 over 5 minus 750 4 over 5, right? So if I didn't have any mistake doing these multiplications, that's what you have. You just need not to add all of this together, and then you will obtain this z component here for the... Don't forget, this is our... This is going to be equal to my bending... my resultant moment. So what is going to happen is, at the end, let me try to copy this, paste. So at the end, what you are going to have is, you are going to have an equivalent system right? So this is your point A. So you will have this equivalent system where the only forces and moments you will have is you will have a resultant of the forces which is given by this vector here. Don't forget, this is our resultant of the forces, minus 533 100. I can copy. You will have this for the summation of the forces, and you will have a resultant for the moment, which is going to be 0, 0, and the z component is equal to, maybe I can copy this over there, is going to be equal to 300 minus 100 sine of 30 plus 1000 cosine of 30 minus 125 3 over 2 Sorry, I don't have space there. I need, so minus 125 3 over 5 minus 750 4 over 5. So this is going to be my MR vector. Okay, and then now I can clean this a little bit more. That's it. That's what I want to show you. Oh, so I need to so you will have, okay, you will have, now you can see, you will have an equivalent system in our structure, same structure, but as you can see, everything now is concentrated at point A. You have resultant of the forces, this R vector, minus 533, 100, 0, which is the summation of all the forces, and you have then the resultant of the moments, which is this vector in red, which is given by this vector you have here with component in z direction only. Right? So you can compare the two systems. The first one, this, where you have everything, three forces applied at three different points, and you can compare with this one where you have everything, the resultant of the forces and the resultant of the moments, applied at one particular point, point A. Right? This is very critical. In the afternoon, we are going to do a more elaborated example using this, okay?